So I'll present about observations of Pluto and Charon with James Webb. So the results I will present today have been published in two papers recently, one in Nature Astronomy and one in Astronomy and Astrophysics. So the two observations I will be talking today are part of cycle one, led by Emmanuel Lelouch. So there is a MIRI imaging observation of Pluto and Charon to get light curves in the thermal infrared. So there have been in the past observations in the infrared in photometry with Spitzer and Herschel, but Pluto and Charon were not separated, were not both resolved due to the PSF. They were merged. So here with James Webb, we are able now to separate Pluto and Charon and get for the first time a thermal light curve for each of them. So this enables us to determine the thermal emission of Pluto and of Charon separately. And then the second observation I will be presenting is a deep MIRI MRS spectrum in the infrared of Pluto's atmosphere. And this is the first time we can see that with James Webb because Pluto's atmosphere is so cold, up to 100 Kelvin, than the previous instrument didn't have the sensitivity to observe Pluto's atmosphere in this wavelength range. So with James Webb, we can now open this range of wavelengths. So with these two observations, there are specific ideas we want to test. First is the fact that the haze on Pluto may control the atmospheric temperatures, the thermal structure. In this case, it should have a strong thermal emission. So that's something we can test with James Webb. And second, there have been a paper by Panayotis Lavas showing that Pluto's haze may have a strong contribution from the hydrocarbon ice, in particular C4H2. And this is something also we can test with our observations. Finally, in this proposal, we also had near-cam filter imaging to map the albedo and the volatile ices, but this observation actually failed. It was poorly designed, and we actually saturated Pluto. But the bonus is that we were able to get the data from NICS and IDRA, which detected, and I think Brian Holler has a talk about that on Friday. And also there were a MIRI LRS spectrum of Charon, but I will not cover that today. We didn't see much apart from water ice on this spectrum. So this is just a slide showing for the photometry with MIRI the data to illustrate the data reduction and the PSF fitting. So you see Pluto and Charon. And once we do this PSF fitting and data reduction, we can obtain light curves. And so you see here the light curves we obtain for Pluto and Charon at 4 wavelengths of 15 microns, 18 micron, 20 micron, and 25 micron. And you see that Charon dominates over Pluto, except at 15 microns, where Pluto dominates because you still have a contribution for the solar reflected and atmospheric emission. Okay, so now we analyze these light curves with a thermophysical model. So one for Charon, taking into account the albedo map. And for Pluto, of course, we need to take into account the sublimation and condensation of the volatile ices, such as nitrogen and methane. So in both models, the three parameters that we have are the surface emissivity and the surface diurnal thermal inertia that we are trying to retrieve. So I start with Charon. This is the best fit model that we have. The data is in black here, and the model is in red. For Charon, we use the two terrain models. So we have one terrain for the dark pole and one terrain for the water ice. And we can retrieve here the diurnal thermal inertia and the emissivity. So you have the values here. Overall, we find a low thermal inertia for Charon and high emissivity. And this tells us that the surface temperature on Charon must be relatively cold, and it goes in the sense of cold North Pole and South Pole, able to trap methane molecules and lead to tollins productions as explained in Grundy et al. 2018. So we can have a rough estimate that 10 centimeters of tholins have been created over 4 billion years if we take the estimates from Grundy et al. For Pluto now, this is the data that we have. So we have the flux, but here we look at the flux contrast because we assume that the surface emission varies with longitude, but the haze emission does not vary with longitude. We assume that the haze is well mixed in longitude. That's why we first fit the flux contrast with the model of the surface, and then we look at the haze emission when we look at the absolute flux. So in this case, we retrieve values for methane emissivity and global thermal inertia that are consistent with previous estimates from Spitzer and Herschel. And we have some estimate for the surface temperature of methane as well. You see that we obtain a very good fit of the data. And then we look at the absolute flux, and you see that we need a large contribution of the haze that you see here to explain the total amount of flux that we see at 18, 20 micron and 25 micron. So the take-home message here is that there is a large contribution of Pluto's haze in the observed mid-infrared flux. This figure shows you the mean haze flux versus the wave number or wavelength. You see our points here, and we used a 1D model of the haze to estimate the haze emission, and depending on different optical constants that we can use. So you see we use optical constants for tholins and also a mixture tholins plus ice. And overall, we find that the mixture of tholins plus ice is a good sample to explain our haze flux here, and also the increase of flux we get at 15 microns. And when we look at the heating and cooling rate that this implies, we find that in any case, the haze cooling rates that you see here are much larger than the gas heating and cooling rate. So this confirms the hypothesis of Zhang et al. In 2017, the fact that the haze dominates the thermal structure because the cooling rates and heating rates are 2 orders of magnitude larger than the gas heating and cooling rates. So the haze really controls Pluto's climate in general. Now I'll talk with the MIRI MRS spectrum. So you see here, this is the spectrum that we obtained with the 8-hour observation of Pluto. You see it's a fabulous spectrum that we see here with many things that we can see, many process. It highlights many processes of Pluto's atmosphere and surface. You see here a zoom on the broadband absorption of surface ices, of course, methane ice. But we also detect for the first time CH3D and ethylene ice here. In terms of atmosphere, we find gases that were expected, such as C2H6 and C2H2 that were observed by New Horizons as well. We use the photochemical model to try to derive the abundance. And here it is as expected, meaning that we find the abundance that were expected. We also detect CH3, C2H, and C4H2. Here we were expected, according to the photochemical model, stronger absorption, and we find weaker absorption. So this is to be investigated in more details. And overall, we also find methane and CH3D emission bands. And this was not expected at all, because at this wavelength, the contribution should have been negligible, which means that what we see here is not thermal emission. It's a non-in-equilibrium. It's non-equilibrium thermal emission. So it's fluorescence that we see, that the methane molecules are excited by solar photons and reach upper levels, and then that they excite and emit a photon. So that's what we are seeing here. So just for astronomical context, here this is a spectra of Titan taken 30 years ago, and by ISO, and you see that the spectra here resembles the spectra I just showed you on Pluto. it's a spectra of similar quality with the bands of different hydrocarbons. But if I come back to my Pluto spectra, you see that the flux here is 1 millijansky, and the flux here on the Titan spectra is 100 Jansky. So it means that James Webb is able to do what ISO did 30 years ago, get a spectra of similar quality, but with a flux that is 5 order of magnitude weaker. So this is just incredible. Okay, so very quickly, Emmanuel Lelouch et al. Worked on analyzing the fluorescence. So they use an empirical model to fit the different bands of methane on CH3D. So for now, it works pretty well when we do it empirically, but we are working now on adapting with the models that really take into account the physics of the excitation of the molecules. So we can derive the overage ratio, but it's not robust yet. We are really waiting for this more physical model. And finally, when we look at the band due to the haze in the infrared, we are trying to look at which optical constants of tholins or ice can match these bands. And we find that these bands can be explained by benzene and C4H2, which was also expected from photochemical model. So the agreement is not perfect, but the position and shape can depend on ice mixtures and temperatures. And when we compare to Titan, so it's not like Titan. Titan doesn't have much ice in its atmosphere, except in the polar vortex, where benzene was also detected. You have a lot of hydrocarbon clouds there. So overall, what it means is that our detection supports the hypothesis by Lavas et al. That Pluto's haze has a strong component of ices, and probably benzene and C4H2 are the main component. Okay, this is my summary slide. So I leave it here and I'll take questions.
Thank you. Do we have questions for this paper?
So thank you for that, Tanguy. Your conclusion in bold strongly impacts the climate. Does it really impact the surface temperature? And let me put it a different way. If there was no haze, would Pluto's surface temperature distribution be any different?
No, in terms of surface temperature, it doesn't have a strong impact. The atmosphere remains too thin to have an impact on temperature in general. The only impact I can see is that if you have a lot of ice particles, it's going to sedimentate and darken the surface. But in terms of just impact of temperature itself, it has no impact.
Thank you.
Thanks. Really amazing data. With respect to seeing the emission from the haze and confirming that the haze is most likely the agent that keeps the upper atmosphere cool, I wonder if there's any chance of following up on Sitang Fan's paper on a bimodal distribution of hazes. And he said we should look for 2 different temperatures of emission. Do you think there's any chance of resolving the haze emission further?
That seems complicated to me, but it's working. We are working currently with Bruno, which is the next talk, with haze model in 3D. And we do have fractal populations, spherical populations. So with this model, we may be able to extract different emission depending on the type of particle population. So maybe we'll find something interesting, and then we'll think how we can observe it or confirm it by observation.
Chris Klein, Southwest Research Institute. Great talk. I love the data. So I have one comment and one question. The comment is, I know you caution that the D to H is tentative, but it's really interesting that it looks like it could be 2 times terrestrial, which is intriguingly similar to Eris and Maki Maki from Will Grundy last year.
Right.
So there might be some kind of common theme that we're still trying to piece together about methane on these large KBOs. That's a comment. The question is, I really enjoy the comparison to Titan spectrum. I noticed that HCN is found there. Do you see HCN in Pluto's atmosphere?
Yes, we see HCN
It's in the mirror.
because atmosphere, but it was old observations.
That's ALMA. Is it?
Yes, with ALMA. Not in this one, we don't see HCN.
Okay, interesting. Thanks.
And just for the comment, I think I had a slide about D over H ratio. Yep, that's one, the last one. And so you can see that we also have a detection in situ H2 gas, and we would like to work on the detection of this D over H in the methane ice as well, but we don't have the optical constant at this wavelength, so that's something we will be interested in. So there is probably a story, but for now, as you can see here, it's still ambiguous on Pluto, but as you can see, we have more than I showed before.
Let's thank the speaker again. I'm sorry, we're out of time.